Earlier, we said that a game is basically a situation where there are players. These players will take some action and that will result in the outcome of the game. But now the problem is if these players have different preference on the outcome of the game, then how should these players play the game? Should they compete? Should they cooperate? So what strategy should they use? And now the person that comes up with the answer to this question is the John Nash. So this guy is the person who is considered as one of the founding fathers of the game theory here. So the way John Nash answered this question is that, well, instead of looking at what each player should do, he looked at the overall system and he said that the overall system is an equilibrium. For now, I'm just gonna call it a pure strategy Nash equilibrium if when each player play the strategy profile. So here this is the strategy from the end player. So this is the from player 1, play S1, and then player 2, play S2. So let me use different color here. Let's say player 1 play S1, player 2 play S2, and so on. And then the last guy, player N play Sn. So I look at the overall pictures of how all the different players play the game. So I'm gonna say that this collection of strategy or the strategy profile is a pure strategy Nash equilibrium if no player benefit from changing these strategies. So once everyone agree on how this is we're gonna play the game, then no one should change their mind. So if they change their mind, it's not better than what they agree on at the moment. In other words, what that means is when we end up at the Nash equilibrium here, there is no incentive for the players to cheat or to deviate from the strategy that we have. So let's look at the examples that we have down here. Examples 7.1. So these are all the games that we looked at in the last lectures, by the way. But let's take a look at it again. So let's say, so this is gonna be a game between Alice and Bob again. So Alice is gonna choose between the top row or the bottom row, and Bob is gonna choose between the left column or the right column. And let's try to see if S1 and T1, S1 and T1, is this a pure strategy Nash equilibrium? And if we look at it, let's say if Alice say, hey, I'm just gonna play S1, and Bob say, hey, okay, sure, I'm gonna play T1. But now, when Alice look at this strategy profile, Alice can say that, maybe, if I play at the bottom row, it's gonna give me more money because, well, if I play up here, I'm only gonna get $1. But if I change my mind and I cheated from what we have here, I'm gonna get $3. That's the better option. So this guy is not pure strategy Nash equilibrium. So this is not pure strategy Nash equilibrium. So pure strategy Nash equilibrium. Nash equilibrium. So from now on, I'm just gonna write this as PSNE. Okay. So now, is this thing S2 and T1, is this a pure strategy Nash equilibrium? So we can kind of see if Alice say, okay, I'm gonna play S2, and Bob say, okay, I'm gonna play T1. Now, if Alice change her mind later, and play S1 instead, notice how, well, Alice, she originally, okay, let me kind of highlight it here. Originally, Alice would have gotten $3, but if Alice changed her mind, then she only got $1, so there's no reason for her to do so. So here she sticks with her choice, which is S2. And now, for Bob, he said that, well, if he plays T1, then he's gonna have to lose $3. Remember again this number 3 here? This is the outcome for Alice. That means Bob will pay Alice $3. So that means Bob will lose $3. But if he changes his mind and play T2, that means, well, he's gonna lose $4 now. So he's in a worse off situation. So there is no reason for Bob to change his mind. So in this case, we can say that this strategy profile that Alice and Bob say, okay, I'm gonna play S2 and T1. This is indeed the pure strategy Nash equilibrium. Because no one is better off playing the other options. And this is also the same number that we get from the example in the last lecture. let's take a look at this example here. So let's say we once again have Alice and Bob. So let's say, for example, if Alice say I'm gonna play S2 and Bob say, okay, sure, I'm gonna play T2. Is this Nash equilibrium? So let's say I have S2 and T2. Well, notice how if I am Alice, so if we put ourselves in Alice's shoes, we see that, well, if Bob were to choose T2, then there's no reason for me to pick the bottom row. I can just pick the top row because I'm gonna get more money now. So this is not pure strategy Nash equilibrium for sure. Or we can put ourselves in Bob's shoes as well. So Bob can say, well, if Alice is gonna play bottom row, then there's no need for me to play T2. I'm just gonna play T1 because originally I would have, so if it ends up here, that means nothing will happen. So no one pays no one. But if Bob changes his mind and play T1, that means Alice will now have to pay Bob $3. So Bob better change his mind. So this guy is not pure strategy Nash equilibrium. But if we look at S1 and T1, so end up here, S1 and T1. Again, well, if we put ourselves in Alice's shoes, we can see that, well, getting $1 is better than losing $3. So if Bob were to say that he's gonna pay T1, then there's no need for me to change my mind. I better get this $1 here. And that's the same for Bob. If Bob changed his mind, so instead of losing $1, he's gonna lose $2, or he's gonna lose $3. So yeah, though there's no reason for Bob to change his mind, so this is already the best option for Bob. So this is indeed pure strategy Nash equilibrium. So there's no reason for either of the players to change their mind. And now for the last one. Well, let me just say, so let's say if S2 and T2, let me just pick something. So let's say I have Alice here, and then we have Bob here. Yeah, so is this thing a pure strategy Nash equilibrium? And we can kind of use the same reasoning again. So if Alice plays S2 and Bob plays T2, then we will end up at 0. Now then, Alice can think to herself, wait, give me a second. Okay, so if Alice look at how she should play the game, and she can see that, well, if Bob is gonna choose T2, then I better choose S3 because then I'm gonna get $10. And now Bob can say the same thing. Bob sees that, well, if Alice were to choose S2, then maybe I should play T1 instead, and that's how I can get $1. So this guy is not pure strategy Nash equilibrium. But on the other hand, let's say if Alice were to play S3 and Bob were to play T1, and then the outcome would be this thing. This would indeed be a pure strategy Nash equilibrium. S3 and T1. This is indeed pure strategy Nash equilibrium. And we can see that, well, if Bob were to play T1, then Alice has no reason to change her mind. Maybe, well, I mean, she's not any better off playing any other options anyway. She's gonna have to pay Bob $1 no matter what she chooses. Yeah, so there's no reason for Alice to change her mind. And now if we put ourselves in Bob's shoes, then changing strategy only results in a worse off option. So he will have to pay Alice $1, he will have to pay Alice $10, but if he sticks to his choice earlier, then he gets $1 for Alice. So this is indeed the pure strategy Nash equilibrium. Now let me also remark that the usually I will write S and subscript as the strategy for Alice, and then T with a subscript as a strategy for Bob. But in the notation earlier, I've actually used the S as the strategy for all guys, Alice, Bob, and so on. So this represents the strategy from the N, from all the N players, not just Alice, because if there is N player, then the number of variables could get a little confusing. Now, let me also remark that the pure strategy Nash equilibrium, it is the equilibrium that no player is going to change their mind. But that doesn't mean that the strategy is efficient, and it doesn't mean that it will lead to the best possible outcome. So this is some of the weird facts about Nash equilibrium. So let's take a look at the next examples that we have. So let's say in this game, so by the way, in the two example here, this is gonna be a non-zero-sum game, not a zero-sum game. So Alice will choose whether Alice will choose whether Bob will receive $4 or $5. Bob will choose whether Alice will receive $4 or $5. So Alice will have two options. And so when I say Alice will choose whether Bob will receive $4 or $5, that means that doesn't mean Alice will pay Bob. By the way, that just means, let's say there's like a money in a pot here, and then so this doesn't belong to anyone. It's just like a middle pot. So Alice can choose whether Bob is gonna get $4 or $5. So if Alice pay Bob $4 or $5, she's not gonna hurt herself. So it's not coming out of her pocket. So Alice can choose whether will give Bob $4 or $5. 4 or 5. And then Bob will choose whether Alice will receive $2 or $3. And we can kind of see the payoff for this game already. So if Alice chooses to pay Bob, if Alice choose 4 and Bob choose 2, then that means Alice will get $2, Bob will get $4. In this option, Bob say that Alice should get 3 and Alice say that Bob should get 4. So it's going to be 3, 4. And then for the bottom row, Bob is going to get 5, Alice is going to get 2, so this is 2, 5. And the last one is 3, 5. So again, I have two numbers here because this is not a zero-sum game. They both are going to win money from the pot here. Now, one weird thing about this game is that all PL strategies, or in fact, all strategies are indeed pure strategy Nash equilibrium. Now you can, if we think of it this way, so if let's say Alice choose the first row, and then Bob will choose, and then let's say Bob choose the first column. So that means Alice say, well, Bob should get $4, and Bob say Alice should get $2. And this is what they end up with. And that's what we just said. So Alice get 2 and Bob get 4. Now, this is a pure strategy Nash equilibrium because if Alice were to change her mind, then notice how in the earlier option she get $2. So Alice get the first number, Bob get the second number. If she change her mind, then she still get $2. Well, Bob get more money, but she doesn't care, she get $2. So that means Alice has no reason to change her mind. So Alice can just say, well, I'm just gonna give you $4. And that's the same with Bob. If Bob change his mind, so Bob get the second number. So if Bob change his mind, sure, Alice will get more money. Instead of Alice getting $2, now Alice is gonna get $3. But Bob will Bob will still receive $4. So Bob doesn't get anything better from changing his mind. So we say, who cares? I'm just gonna do this. So this 4 and 2, this is indeed a pure strategy Nash equilibrium. No one has any reason to change their mind. But we can kind of see how this is not the best possible outcome. The best possible outcome is kind of what we have down here. So if Alice were to choose the bottom row and Bob were to choose the left column, then they would have gotten more money out of the pot here. So this could happen when we talk about the Nash equilibrium. And now for the last example, this is indeed the famous example. This is one of the examples that kind of give the that kind of make Nash equilibrium thing famous. This has a name. This is called the prisoner's dilemma. So let's say Alice and Bob, they are suspect of a crime. So they found Alice and Bob together in a crime scene, but they have no evidence. So what they decide to do is that they put Alice and Bob in a different room, and they interrogate Alice and Bob. So Alice and Bob have the option to either confess or remain silent. Now, if they both don't say anything, so if Alice don't say a thing and Bob don't say a thing, then they get 1 year in prison. So they'll get so I'm just gonna write down -1. So if they don't say anything, then they'll go to jail for 1 year. However, if one person confess, so let's say if Alice confess, and then Bob remains silent, then Alice will go free. Then yeah, because she confessed, so she can go free. On the other hand, because Bob doesn't confess, so he go to jail for 10 years. And vice versa, if Bob decides to confess, but then Alice remains silent, then the one who confessed go free, and the one who remains silent go to jail for 10 years. On the other hand, if they both confess, so if they both confess, then they each go to jail for 5 years. Yeah, okay. So for each player, there's two options, then either to remain silent or to confess. Now let's write this thing out as a matrix then. So each player has two options, either to confess, and let me actually write silent first. They have the option to remain silent or confess. And that's the same for Bob as well. Bob can remain silent or Bob can confess. So once again, Alice choose the rows and Bob choose the column. Now, we kind of see earlier that if they both remain silent, then they each go to jail for 1 year. So the payoff here is going to be -1 and -1. If Alice remains silent and then Bob confess, that means this is the third option here. So Alice go to jail for 10 years and then Bob go free. If Alice confess and Bob remains silent, then that means Alice goes free and then Bob goes to jail for 10 years. And if they each confess, then Alice go free. Alice and Bob, they each go to jail for 5 years. Now, let me also say that sometimes when you look at the textbook in game theory, sometimes they could also write this table a little differently. Let me also kind of rewrite that here. Sometimes instead of writing these payoff as a vector, as a number pair, sometimes they actually write it in a triangular cell, kind of like this. So Alice has the option to remain silent or confess. Bob can choose to silent or confess. And then the number that you see, you can kind of see the number that goes in the bottom triangle. This will go to Alice. And the number that goes in the top triangle, this will go to Bob. So I can kind of write the same matrix this way. So for the first row and first column, it's going to be -1, -1, and this is -10 and 0, and this one is 0 and -10, and this is -5 and -5. Yeah, it's the same thing, just written in a different way. So now let's try to analyze this game. You can kind of see that the best option that they should choose is that they should remain silent. So then, well, they just go to jail for 1 year. But if we try to analyze this, so Alice remains silent and Bob remains silent. If this a Nash equilibrium. Now, if we put ourselves in, let's say, Alice's shoes first. So Alice think, well, if Bob remains silent, then maybe I should change my mind and confess, because that means, well, if Bob remains silent and I also remain silent, then that means I'll go to jail for 1 year. But if I confess, then I just go free immediately. Yeah. So if Bob were to remain silent, then there's no need for me to remain silent. I should just confess and then go free. On the other hand, Bob can kind of see this, and he kind of reasons with himself, wait a minute, if Alice is going to confess, then that means I'm gonna go to jail for 10 years. And that sucks. Maybe I should also confess as well, because that means instead of going to jail for 10 years, I'll go to jail for 5 years. And this, indeed, is the pure strategy, is the only pure strategy Nash equilibrium for this game. Is the only pure strategy Nash equilibrium for Prisoner's Dilemma. In fact, you can also state some another result, which is that for both players, confess actually dominate. So it actually is the case that the confess dominates the silent for both players. For example, what I mean is playing confess is always a better choice than playing silent no matter what the other player does. For example, if Bob were to remain silent, well, we see this already. If Bob were to remain silent, if I have to choose between the two options, then I should just confess because then I can go free. I'm talking about Alice now then. So if Bob were to remain silent, we put ourselves in Alice's shoes, then we should just confess and then go free. On the other hand, if Bob confesses, then I have to choose between going to jail for 10 years or going to jail for 5 years, and then go to jail for 5 years is a better option. So if Bob confesses, I should confess. So what that means is no matter what Bob does, Alice should always just confess. So even though we kind of see that to remain silent for both players, this is kind of the better outcome for the society. But by the principle of domination and by the Nash equilibrium, the theory seems to suggest that, well, it will end up that both player is going to confess because confess dominates silence, and then to confess for both player, this is the only pure strategy Nash equilibrium for this game.